today we shall learn how to design staircases. So far we have done that slab, design of slabs, design of beams, design of columns and design of footings. So one of the important element in any building or any structure, that is staircase, because that one only will help us to go from one floor to another floor. You will find out different kind of staircases. We can say, and this is our that lecture number 26, which we are going to deliver on design of staircases. This is one type of staircase. You will not find out many, but this is one type. Sometimes in your campus also you will find out few of them. This is the same view, the different view of the same structure. So you can find out as if the staircase, you can say as if that bricks one after another, it is just kept and you are just going from the one floor to another floor. This is another type. Compared to the other one, you see this is another type. Here I think I can show you. This is your steps, and where you can find out one, that beam. In the back there is a beam, and this beam is supporting, I think the last view will be better. Yes, here there is a beam here, and over that your all the steps are supported. So obviously the first one which I have shown, that is one kind. This is another kind of say type of staircase which is supported by the beam, and over there your steps are there. So these steps you can say is a cantilever beam again. So that way you can design, but the most popular one, so this is another view, this one. You will find out most of the cases you will find out this type of staircase. This is the most popular one, and we shall design this one. But I shall tell you that how to design other staircases also. What you have to find out, what you have to do for any staircase, what you have to do, that you have to find out what is the governing one, that bending moment, how it is acting, about which axis, and then according to that you have to design, as well as shear force also. So this is your one. So you can say this portion is cantilever, this is your one column, this is another column which is supported by that two beams, one this side, another this side, and this slab. This is the one you have. Okay, I think that's all. I have that photograph so far concerned. So what I can say here, there is one step here. You can see those steps, all the steps. So you have to consider the dead load of that steps also, weight of the steps also. And there is, this is what called waste slab, the slab. So how to design this one? If you would like to say that, I shall not consider this. The first one we have told the steps one after another, but here we are assuming these steps are supported by this slab. So that means I can design that slab. If I now draw the figure, we can say, so this is your slab which we have to design. Over that you have these steps. These are the steps. So what we have to do? We have to design. What about this depth? This is called waste. There are two things. One is that is called rise, R, and this is called tread. So we have, if we make it a very different one in a sense, so I can write down like this. So sometimes it is projected little bit. So let us make it give some certain kind of projection, and then I can go again 2 steps. Yes. So like that it will go. So if we move, and then you have it is supported, these steps are supported by this slab. Okay. So what we have, I can say different components, that dimension. This is W, which is called waste. then one is called from here to here we have trade or T. So, W waste then T trade, then we have R which is called rise, and we have certain portion, this is called nose in nosing, and this portion is called going. So, what we are assuming here in this case, we are assuming that we shall take the dead load of these steps we shall take, but all the things will be supported by this waste slab. This is the most common one. The other cases that as if you are having one, say your beam like this, as if you are having one beam like this, and what you are doing here, then over there are steps, the steps are like this, that is possible, the one I have shown you. So, that is, but that design will be different compared to this one. So, but this is the most common one, popular one. So, let us see that how to design this one. So, now the first question arises, what is the length or that dimension of this rise and trade, nose, going, what is the dimension of that? That is the first one we have. Generally in residential building or factory building, generally what we can do, we can increase little bit that rise, whereas your say public building, that one we make it say maybe 150 millimeter something like that, but whereas in the residential building we can go say 160, 175 millimeter also we can go. But also another one you can say this one, this length and this height or rise and trade, that should be some kind of proportional. If so far that concerned, at least though I should not tell it here, but you should note down that our subway in our that Kharagpur station, there the steps, it is that say little wider, not little, quite wider than the rise, and it is and we feel really discomfort actually. So, that type of proportion also should be there, so that we do not feel any discomfort. But anyway, so let us come. And also compared to your said general load, the general load, if you compare that balcony, it may be crowded, that because say your room or other rooms, wherever that one say your that load, what should be, whereas the balcony it will be crowded more. Similarly, your say the staircase also, that there is a chance, the frequent chance that it will be crowded. So, that is why this load more compared to the standard load on the rooms. So, here, so the first thing that what is the dimension of this rise and trade, and second one what should be the loading. These two things you have to consider in our calculation. So, we can say number one, that dwelling houses, so dwelling houses and factories so if we consider this one, the trade, that one we can take it say 250 millimeter, little less, whereas in the public buildings it will be in the range of trade in the range of 270 millimeter to say 300 millimeter. So, the horizontal portion. What about the rise? So, for public buildings, it will be say 150 millimeter, and factories we can go little higher, 190 millimeter, residential building say 160 millimeter. So we have, this is your rise and this is your trade, or we can say this one actually going. There is a popular formula, generally we write down T, or we can write down in more say G, I think we can go trade, or the total that one we are talking. So G also we can consider here. So now 2R plus G, that one should be greater than say 550 and less than 700 millimeter. We can take it say 2R plus G, that rise plus going, so that we can take say 600 millimeter, that we can take. This is for residential. For any building you can take it, but only because you are changing. So for residential building we shall take 2R plus G say equal to 600. On the basis of that we can calculate. But anyway, most of the cases you will find out say 150 millimeter, 160 millimeter rise, and 250 millimeter or say 260 or 270 millimeter for trade. That generally you can consider, and it is also dependent on, your that. But not necessarily that it is dependent on this formula. We can also say where it is dependent. It is dependent on the center to center of that floors. That means if we have say this is your one floor and we have to go from this floor. So what is the distance, this height, that is very, very important. If it is 3 meter, accordingly we shall distribute. Similarly, we have the length, that size of the room where you have to accommodate. So if this is your height and this is your length, so we have to accommodate here. So depending on that, how many steps you will provide, that also it depends. So not necessarily that we shall keep it within that range. That means it will be within say 250 millimeter, and the other one within say in the range say 150 millimeter. So we can go little higher, little less, 5 millimeter, 10 millimeter, it does not matter. So but it is also dependent on these two things. Now next part is that span, the span of that staircase. So we have to calculate the dead load, live load, and we have to find out the span. So from there we can calculate the bending moment as well as the shear force. So what we generally do, there are few cases. Let us say this is your beam and it is supported like this. This may be one case. So what about this one? What about, and here the steps are here. These steps may be constructed by bricks. So when we have this, so only we shall take the dead load of these steps. So what about your say effective span? This one we shall find out in clause 33, and more specifically 33.1, page 63 of IS 456 2000. So the effective span we generally take it here. For this case we take it here, this one up to this one say x, and this is say y. our code says, and this is your effective span. Our code says, and this is a certain distance, say s. S is the distance. So our code says that if x is less than 1 and less than y also less than 1, if x and y, that means if x and this one is another y, so if these are less than 1, then you take s plus x plus y, that effective span. But if x is greater than 1 or y also and y also greater than 1, then you take s plus 1 meter, for because if x is greater than 1 meter, then you take 1 meter, and if y also say greater than 1 meter, then you take y meter. That otherwise, if it is less than 1, then you take that x only. So here I can say, though it comes that if this is your effective span, I can write down it as s plus x plus y, but our code says that this is your effective span, which you will get it in this clause. So our code says that if x is less than 1, then you take it as x only, whatever value you are getting. Say 0.75 meter, you take it 0.75 meter, 0.8 meter, 0.8 also take it. But if it is a 1.2 meter, then you take it as 1 meter. Similarly for y also. So it should not be these two values, that means s, it should not be more than s plus 2. Okay, so that means now I know what should be our effective span. So if I know effective span, now I have to calculate that your load. What about your load? For residential building, so for residential building we shall consider 2 kilonewton per square meter, and there is a restriction, not liable to overcrowding. That means the staircase will never be overcrowded. But public buildings, they are that balcony and your say that your staircase, that is there, it is very frequent that regular features that it will be overcrowded. So for public buildings, it means liable to overcrowding, and we take it say 5 kilonewton per square meter. So this is your live load. So we have to calculate dead load, and then we have to calculate the live load. So let us come, there is one more case I can say. The first one I have told you, this is one case that already I have told you. It is also possible the one I have shown, that is like this. It could be something, the staircase says something like this. Okay. And either it may be cantilever, the case which I have shown it here, or it may be supported. That means it may have something like this also. So in this case, this is your one type. In this case, what will happen? The effective span here, because we do not have that any such thing. So effective span only center to center distance between, because it is supported by these two beams. The first one we have shown that it is supported here, there is no beam here. Please note, I think you remember. So this is the case where there is no support here, it is only supported in these two beams. It may be supported at walls also, that is another case. But other possible case here which I am talking, there is this one, but here the effective span will be this one, center to center distance, and where you are having the staircase like this. Okay. So, let us calculate dead loads. So, this is your one step, we can take it. This is the one unit of the step which is having, say, your waste slab W, B, and then we have rise R, this is your rise R, the T, the tread, and this portion is going, so we can say the other way, this portion will be same as that going only. So, this is your going, and here also that if we take it, so this one is coming as going, the same portion. So, if we take this one, what about your B then? B will be, B means this one, B will be equal to R square plus G square, and dead load per meter square of horizontal span means along this, that one will be equal to the weight of this one W times B, and we are talking, say, per unit width. That means that we are taking the width of the staircase 1 meter. So, WB, this is your WB times 1 times the unit weight of the concrete plus this triangle, which is half times R times T. R is the, that you will say, height, and T that base, you can say, times the 25 kilonewton per meter cube. This is the 1 meter of width of the staircase, that you can say 1 meter width of the staircase times 25 will give me the weight, and divided by G, this one means kilonewton per meter width, or kilometer per square meter. We are talking the staircase is moving like this, the staircase is going like this. So, I am taking 1 meter width, and we are having the each step. So, each step we can take it. So, that means we can say if you project it, it will go up. So, you will get something that in 3 dimension you will get that this is the unit one, and so I shall get per meter width, I can get it, and this is the weight I can find out, that is the dead load, you can get it. So, in your whole design up to this only different so far the staircase concerned, because if I can calculate the dead load, so now we can consider it as a, say, slab or a beam. So, what is the difference between slab and beam? Slab means only we shall provide the reinforcement due to bending moment, and shear force, whatever it is, that one, that we shall design it such a way that depth we shall increase such a way, so that we need not provide any stirrup, any shear reinforcement. So, then we shall talk it as a, say, slab. But if we provide this one as a, say, your stirrups or thing, that means we are designing at a beam. So, in our case here we shall design it as a slab, because we are not going to provide any shear reinforcement. So, let us take one example, at least let us start today. And this type of staircase is called longitudinal type. So, a longitudinal type of staircase spans a distance of 4 meter. That means it is supported by two beams and the distance between two beams, that is 4 meter. The rise are equal to 160 millimeter, going G 250 millimeter, 250 millimeter, trade T equal to 270 millimeter, and we can consider this one, the trades have 15 millimeter that granulithic finish. So there is one, say, finish over that we are providing, that plates, and consists 16 steps. We are specifying all those things, but for actual case, in the actual problem for a building design, we have to specify this 160 millimeter rise, going, trade, or number of steps that you have to calculate depending on the floor area, floor length, and also the height. So that also you have to suitably you have to adjust and you have to provide, but here we are specifying. So what about the concrete grade? M20 steel Fe415, Fe415, design the staircase for a live load of 5 kilonewton per square meter, and breadth of the staircase equal to 1.5 meter. So we have all the details. The beams, that one, that means it has to span between 4 meter, the rise 160 millimeter, going to 50 millimeter, trade 270 millimeter, that it has a finish, because this was the floor finish, we can say this is the floor finish, but here specifically mentioned we shall take the unit weight of this one, granulithic finish, 23.5 kilonewton per meter cube, that we shall take. The another one 25 kilonewton for concrete, and we can calculate the 16 steps from the going also. Concrete M20, steel Fe415, and live load 5 kilonewton per square meter, breadth of the staircase, that is say your 1.5 meter. So 1.5 meter is the breadth that is given. Number 1, what about the thickness of waste? So we are talking, let us just draw a figure. So this is your thickness of waste. Let us assume span by effective depth equal to 30. We can assume span by effective depth equal to 30, that we can assume, because reinforcement, other things are involved, so we can assume that 30, okay, because there are so many factors are involved, so we can assume 30. So D will be equal to span, how much? Span equal to 4000 millimeter, that's what specified, divided by 30, which comes as 133.33 millimeter. So we can write down total W. This one should be equal to 133.33 plus 15 millimeter cover plus a 12 millimeter dia bar, if we assume that we shall provide, so 12 by 2, which comes as 154.33 millimeter. So let us provide, or we can assume that we shall provide 160 millimeter, because we do not know whether we have to change it. So let us assume that 160 millimeter thickness of waist. After checking only we can provide. So D will be equal to 160 minus 15 minus 12 by 2, which comes as 139 millimeter. So this D, this is your, we have got it from here computed, and finally we are providing say 139 millimeter. Okay. So we are providing 139 millimeter. Now let us calculate the dead load. So dead load from staircase slab and we shall get it on plan. So this is G, this is T, trade, this is R, rise, W, B, and this is G. B equal to root over G square plus R square equal to G equal to, we have taken 250, R equal to 160 equal to 296.81 millimeter, let us say 297 millimeter. Dead load, it will be per meter length of the horizontal one, 1 by G, we have already got it, WB plus RT by 2 times 25 plus F is the floor finish, the thickness, F times T, T is the trade because over the whole trade, divided by G times the unit weight 23.5. So we can get it as G 0.25, W is 0.16, that we have got it 160 millimeter, so 0.16 times B, we have got it 297.297, R equal to that, R we have got it, that rise 160 millimeter, so 0.16 times T is 270 millimeter, 0.27 by 2 times 25. Okay. So we are putting all the values here. Can I manage? Yeah, let us manage it here. So plus 1 by 0.25 times F is floor finish 0.015 15 millimeter times T 0.270 millimeter, 0.27 times 23.5 the unit weight, and which comes as 7.2927 kilonewton per square meter. Okay. So this is all what I am getting here, the dead load, we are getting 7.2927 kilonewton per square meter. What about the design load? design load equal to 1.5 times dead load plus live load equal to 1.5. So 7.2927 already we have computed plus 5.0 that which we have to provide 18.439 kilonewton per square meter equals 8.44 kilonewton per square meter, let us assume. What about the bending moment? Which is here mu. Mu will be equal to that W L square by 10. We shall take it not 8, W L square by 10 equal to 18.44 times that effective span 4 square by 10, which comes as 29.504 kilonewton meter. So we are getting this one. What about the now we have to check that whether the depth we have got it correct or not. So that we can find out as from 0.138 FCK BD square equal to mu. So D equal to root over mu by 0.138 FCK, B equals 29.504 into 10 to the power 6 divided by 0.138 m20 grade times what about B? There are this B, how much will be B here, because we have taken this moment per meter width, bending moment per meter width. Let us make it very specific. Per meter width of staircase, because I have not taken that 1.5 meter, I have taken that per meter width of staircase because I have got it kilonewton per square meter. If we, the one alternative could be that same design load we can take it 18.44 times 1.5 if we multiply for the width of the staircase, then we can directly we can get it. Here we can write down B as 1500, but since I have taken here till now it is 1 meter width, so I have to specify here 1000. Okay, that you please note, and which comes as 103.39 millimeter. So less than 139 millimeter. The other alternative could be that we can calculate mu. That means I know B, I know FCK, I know D, so I can calculate mu. Now this mu, if it is greater than this value, then also you can say it is safe. Either you can check it with the D, you can calculate and you can find out it is less than the D provided. Other alternative that you provide the D here and calculate that moment of resistance of the section, and it should be more than the value we have computed. That way also you can calculate. So now we have to provide steel. So our depth is okay, so we have to provide steel. So where from we shall provide? So you remember this one, 0.36 FCK x by D 1 minus 0.416 x by D times B D square. This is the basic formula from where we have got it. That just let me write down once more, because dividing by 0.36 times 0.416 x by D FCK B D square, if we divide, then we get it 6.68 mu by FCK B D square equal to 2.40 x by D minus x by D whole square. We get this equation, and finally we get x by D equal to 1.2 minus root over 1.2 whole square minus 6.68 mu by FCK B D square times the square root of that. So this is your that formula from where we can get x by d if I know mu, fck, b and d. So when that is the case which we have got it here. So we know mu, we know fck, we know b, we know d, so we can find out x by d. So let us calculate x by d. So 6.68 mu by fck b d square equal to 6.68 times 29.504, that is the moment, to 10 to the 6 divided by 20 times 1000, that is the width, meter width, times the effective depth of the slab, which comes as 0.51. So we can take it that as x by d equal to 1.2 minus root over 1.44 minus 0.51 equals 0.23564. Therefore, z equal to d times 1 minus 0.416 x by d equals 139 1 minus 0.416 times 0.23564 equals 139 times 0.9019. Please note, because why I have written this one, I can put the value, but please note that 0.9019. That means generally it comes a 0.85 times d, 0.95 d. If you do not, sometimes what we do, if we do not know that, say we would like to calculate the area of steel. So from our experience we can find out that z, the lever arm, we can take say 85% of the effective depth or 95% of it. That means that is the range. That's why I have written here that what could be the range, that also you should note. When directly we do not want to calculate all those things, you have no calculator, but we would like to calculate say at site itself, we would like to estimate. So that way also you can find out. So which comes as 125.36 millimeter. So z we have got it. So what about the area of steel then? Area of steel will be equal to mu by 0.87 fy times z, which comes as 29.504 into 10 to the power 6 divided by 0.87 times 415 times 125.36 equals 651.86 millimeter square. So what about the total steel? This is per meter width. Equal to 651.86 times 1.5 equal to 977.79 square millimeter. So we can provide here that number of bars 977.79 divided by 113 12 torr equals 8.65. So provide 9 numbers 12 torr. What about percentage of steel? 9 into 113 divided by 1500 into 139, this is the width I am talking, and into 100 equal to 0.48 percentage. So percent of steel you have got it 0.48. Okay. So we know the steel and we also know the that effective depth. Now we have to provide the distribution steel. So distribution steel, that one will be equal to 0.12%. S equal to 0.12 by 100 times, we can say 1000, that is the 1 per meter width, times 160 overall depth, comes as 192 millimeter square, provide 8 torque at the rate of 250 millimeter center to center. So area of steel provided 200 square millimeter. So we can provide 200 square millimeter. Now what about the shear? We have to check for shear, because after this we have computed so many things so much, but after this if we find that shear stress it is more than the permissible, then we have to change the section. So shear force V will be equal to WL by 2 equal to 18.44 times 4 divided by 2 equal to 36.88 kilonewton. So tau V equal to 36.88 into 10 to the power 3, thereby we are talking this one per meter width. So 1000 times 100. Please note that which one you are putting the values, if it is per meter width or taking the total width. If it is total width, then in that case you have to provide here 1500, but here this 18.44 per meter width. So which comes as 0.26 Newton per square millimeter. So even then this one with the 0.15% steel, we can get it for 0.48% of steel from that table 19 of IS 456. I can find out what is the permissible. Even if I take say 0.15%, which is coming less than 0.28. So 0.28 Newton per square meter for the bare minimum in our code that provided, that is for 0.15% of steel. Even that is less than that. So we need not change the section. So it can take care of the shear force. Now what about the deflection? So this deflection we shall check it from the point of view of L by D ratio. From the point of view of L by D ratio. So we shall get it as percentage of steel provided, that is 0.48. So if we now go back to that table or figure, just for your reference, that is in figure in the IS code, that is in figure 4 of 38. We shall take this one, say your continuous beam or continuous slab, WL square. We have not taken WL square by 8, WL square by 10 we have taken. So if we take say 0.38, that continuous, then we shall take minimum one L by D, that is say 26. 26 is the L by D ratio. So we shall take L by D ratio, that is say 26. But it is for continuous. That one you will get it in clause 23.2.1, where it is given that basic values of span to effective depth ratios for spans up to 10 meter, cantilever 7, simply supported 20 and continuous 26. We are taking continuous here, we have not taken WL square by 8, so we will write it as 26 for continuous. And so what we can do it here. Now what about the modification factor? There are so many others, but I shall take it from figure 4. So FS, we have used how many bars? 9 bars of 12 millimeter dia, each of them 113 square millimeter. We have to provide 977, that is the one we have to provide. We have to provide 977, isn't it? That we have computed 977. 977 we have computed. So 9 into 113 times 0.58 FOI times 415. So that is your FS, and which comes as 246 Newton per square millimeter. So I shall get it from figure 4. This is from figure 4. If I show you, this is figure 4 in page number 38. In figure 4 there are so many curves. there are so many curves in figure 4. So, I shall take the corresponding one, interpolate it, and which will come in as for 246, that f2 the factor that is comes as 1.2. So, if you, this is from just for your reference, figure 4 page 38 of IS 456 2000. Okay. So, we shall get it multiplication factor 1.2. So, allowable L by D equal to 1.2 into 26 equal to 31.2, and we have assumed L by D, that is 30, which is less than 31.2. So, we can find out, that means it is acceptable, this is okay. Okay. So, one more checking is there, and that is related to your say crack, and that how should, there are two things, that is your, these are coming from serviceable limit state. One checking is coming from the L by D ratio, and other checking will come from the spacing. So, you have to check the spacing whether it is less than 3D or not, and obviously whatever we have provided, say 9 bars, if you, which is provided in 1500 millimeter, you will find out that is less than 3D. Similarly, for the distribution steel, whatever we have provided, so that one also you will find out that 250 millimeter, which is less than 3D. So, that means from the cracking point of view also we can say it is all right. So, now we have to do the reinforcement, and that we shall do it in appropriate place. Okay. Thank you.